Dear students, in this session we will discuss the closure properties of context-free languages. First of all, we will discuss what do we mean by the closure properties. Closure properties are nothing but the operations over the members of some set which are guaranteed to produce a member of the same set as the result. From this definition, we can understand that suppose if we take a set of positive numbers and if we perform an addition operation over some of the members of this set, then result will always be present in the same set. Result will always be a positive number. So that's why set of positive number is called closed under the addition operation. And this addition operation is called one of the closure properties of this set of positive numbers. So in this manner, we define the closure properties. Now we'll be discussing many important closure properties of context-free languages. Now we discuss our first operation which we can perform over the context-free languages, that is the union operation. Okay. So suppose we are having a language L which is the union of two languages L1 and L2. And let us assume that both L1 and L2 are context-free languages. So if both L1 and L2 are context-free languages, our claim is that L is also context-free language. So we will be proving this closure property with the help of the construction procedure. So if L1 and L2 are context-free languages, then we will be able to write a context-free grammar corresponding to it. Okay. So let us assume corresponding to L1, G1 is the context-free grammar, and corresponding to L2, G2 is the context-free grammar, where G1 is defined as V1, Sigma 1, P1 and S1. So V1 is the set of variables in G1, Sigma 1 is the alphabet over which the language L1 has been defined, and P1 is the set of productions in the grammar, and S1 is the start symbol of the grammar G1. And similarly, V2, Sigma 2, P2 and S2 are variables, alphabet, set of production and start symbol of the grammar G2, which is representing the language L2. So both are context-free languages. Then we can form a grammar G such that the set of variable of the grammar G is S union V1 union V2. We should write like this, S, because it is a set. So V1 is a set, V2 is a set, and S is a set containing only one element, S. Okay. So this whole set will be the set of variable, that is Vn, for this grammar G. Okay. And then Sigma 1 union Sigma 2 will be its alphabet, because it will be consisting of all the words which are represented by L1 as well as L2. So Sigma 1 union Sigma 2 will be the set of alphabet for this new language G. Okay. And then P will be the set of productions. We will be discussing how we will define P, and S will be the start symbol. So this new symbol S which we have introduced will be the start symbol of this grammar. Then P we have to define as P1 union P2, means all the productions of the grammar 1 will come. P2 means all the productions of the grammar 2 will come. And then we will be adding one more production of the form S2 S1 oblique S2. Okay, so this is a well-known technique which we have already discussed when we have discussed the design of the context-free grammars. So what we can do is, because S is the start symbol, so from S we can either move to S1 or we can move to the S2. S1 is the start symbol for the grammar 1. So starting from S1 we can derive any word which is in the language represented by the grammar G1. And similarly, if we reach to S2, from S2 we can reach to any word which is part of the language represented by the grammar G2, that is the L2. Okay, so that's why we will be able to generate all the words in our grammar G, by our grammar G, which are either in the L1 or in the L2. Now come on our second operation, that is the concatenation operation. Suppose we want to define a language L is equal to L1 concatenation L2. Means L will be consisting of all the words such that first part of the word will be from the language L1 and the second part of the word will always be from the language L2. And both L1 and L2 are context-free languages. So because these are context-free languages, so again we can define the grammar corresponding to these as we have discussed in the previous union operation. So G1 is the grammar corresponding to the language L1 and G2 is the grammar corresponding to the language L2. Then we can always define another grammar G such that the set of variables of this grammar G is the union of V1, V2 and the new variable S, as in the previous example. And the sigma, that is the alphabet for this new grammar G, will be the union of both the alphabets, that is sigma 1 and sigma 2. And then P will be defined and S will be the new start symbol. And P will be defined by the union of all the productions of P1, all the productions of P2, and then one more production of the form S2, S1, S2. Okay, so from S1 we can always generate a word in the language L1, and from S2 we can always generate a word in the L2. So we will be able to generate the words of the form in which first part is coming from the language L1 and the second part is coming from the language L2 from the start symbol S. So in this manner, we can generate a grammar corresponding to L. So that's why our concatenation operation is also closed under the under the context-free set of context-free languages. So it is also one of the closure properties of the context-free languages. Now come on our third operation, that is the closure operation, meaning thereby that L is equal to L1 asterisk, where L1 is some context-free language. Okay, so it is represented by the grammar G1 such that G1 is equal to V1, sigma 1, P1 and S1. Then we can always define the grammar G corresponding to the language L such that its set of variables Vn is S union V1. So all the variables from V1 including the new variable S will be the part of its set of variables. And then it will be defined over the same alphabet, that is the sigma 1. And then set of production will be P and S will be the start symbol, where the set of production P is equivalent to P1 union S to SS1. So one production of the form S to SS1 will be included and another production S to null will be included. Through the introduction of these two productions, we can generate S1 any number of times, because suppose S is equal to SS1, so first time it will be SS1, then again we replace S by SS1, so it will become S1. So we have generated S1 two times. So in this similar manner we can generate S1 any number of times, and ultimately we can remove S by null. So in this manner we can generate a word which is the combination of many words, and each word is coming from the language L1, because S1 is a start symbol for the grammar G1, so it is generating the L1. So each S1 will generate a word in the language L1. So our word in the language L will be the combination of many words from the language L1. So in this manner we can generate L1 asterisk. So closure is also one of the closure properties of the context-free languages. So our context-free languages are closed under the closure operation as well. Now let us come on our fourth operation, that is the reversal operation. Suppose L is a language which is a context-free language, then we want to see whether LR, the reversal of it, will also be a context-free language or not. Okay, so let us assume that L is equal to LG, and as it is a context-free language, so we will be able to write a grammar G corresponding to it. Suppose grammar G corresponding to it is having the V, T, P and S set of variables, set of terminals, set of productions and start symbol. Okay, then we can always construct another grammar GR, which will be having the same set of variables, same set of terminals, same start symbol and all the productions which are the reverse of the productions in P. So each production in PR is the reverse of one production in P, meaning thereby if A2 alpha is a production in P, then A2 alpha R will be present in PR. For example, suppose my alpha is BC, okay, then alpha R will be CB, okay. So if A2BC is a production in P, then A2CB, the reverse of it, will be a production in PR. So in this manner, I will be defining the productions in PR. If I do like this, then essentially all the centennial forms in this grammar GR will be the reverse of all the centennial forms in the grammar G. So in this manner, we can define the language LR, which is consisting of all words which are the reverse of the words in L. So that's why reversal of a context-free language is also a context-free language. So it is context set of context-free languages is also closed under the reversal operation. Now come on our next operation, that is the intersection operation. Intersection operation means that our language L will be the intersection of two languages L1 and L2, and we assume that both L1 and L2 are context-free languages. Then under the intersection operation, our CFLs are not closed. So up till now, whatsoever operations we have discussed, under those operations, our CFLs were closed. Okay, so those were the closure properties of the context-free language, but under the intersection operation, our CFLs are not closed. So this we will be showing with the help of an example. You just see that the language L is equal to 0 to the power n, 1 to the power n, 2 to the power n, such that n is greater than or equal to 1. This language is not a CFL because three quantities we are matching simultaneously. So that's why this language L is not a CFL. It is not a CFL. Now we will show that this language is the intersection, is the result of the intersection of two languages, which both the languages are context-free languages. So L is, I am rewriting it in the form 0 to the power n, 1 to the power n, 2 to the power I, such that n comma I greater than or equal to 1, means in this language, number of zeros and number of ones need to be equal, but any number of twos may come greater than or equal to 1. Okay. In the second language, number of zeros are maybe arbitrary. Okay. But number of ones and number of twos should be equal. 0 to the power I, 1 to the power n, 2 to the power n. So number of ones and number of twos should be equal. So this language is saying number of zeros and number of ones should be equal. This language is saying number of ones and number of twos should be equal. And if we take an intersection of this, means we want the words which are common between the two languages, means where the number of zeros and number of ones should be equal, and here number of ones and number of two should be equal. So if we take an intersection, means we want all the number of zeros and number of ones should also be equal, and number of ones and number of two should also be equal, meaning thereby all number of zeros, number of ones and number of two should be equal. That is equivalent to this particular language, 0 to the power n, 1 to the power n and 2 to the power n. Is it? So this is a intersection of these two languages. Now these two languages both are context-free languages. This we have already seen. We have made a grammar corresponding to it. If we want to form a context-free grammar corresponding to this language where number of zeros and number of ones are equal, then we will be forming it in the form of S2 xt. So this we will be generating through x, and this we will be generating through t. Is it? So through x we will be generating 0x1 any number of times, and then ultimately replacing x by 0, 1, because n is greater than or equal to 1. Then from t we will be generating 2t any number of times, and then we will replace t by 2 because I is greater than or equal to 2. So in this manner we can write this grammar for this particular language, and we can see that this grammar is a context-free grammar. Similarly for this as well, we can write the grammar. We can write the grammar in the form of S2ZY. So this is Z and this is Y. Okay. So from Z I can generate 0Z and ultimately replacing it by 0. So any number of more than 1 zeros I can, 1 or more zeros I can generate through Z. Similarly from Y, 1, Y2, and each time I will be using it, the equal number of ones and twos I will be able to generate. And then y I will be replacing by 1, 2. So in this manner I can generate equal number of ones and twos. So this is also the grammar which is the context free. So both the language, our L2 and L1 are context free languages, and their intersection is this L, which is not a context free language. So through one example we have shown that if we take two context free languages and take their intersection, it is not always true that the result will also be a context free language. It may be context free in some of the cases, but not in every case. So, okay, so because it is not true in every case, so under the intersection operation, our CFLs are not closed. Now come on our next operation, that is the complement of a language, that is L complement. So if L is a context free language, we have to test whether L complement will always be context free or not. So to test this, we will first assume, suppose L complement is always a context free language when L is also a context free language. Means under the complement operation, we are assuming that L complement is closed. Okay. So let us check L1 intersection L2 through the De Morgan's law. So it is L1 complement union L2 complement and the whole complement. Okay. So because L1 is a context-free language, so L1 complement is also as per our assumption. L2 is a context-free language, so L2 complement is also a context-free language as per our assumption. So both L1 complement and L2 complement are context-free languages, so their union will also be a context-free language as we have already proven. So this L1 complement union L2 complement, this language is a context-free language, then its complement will also be a context-free language. Meaning thereby, this whole will be a context-free language. And it is equivalent to L1 intersection L2. And we know that we have just proved that L1 intersection L2 is not always CFL. Meaning thereby, this is a contradiction. This is a contradiction. Now we know that we have used only two operations here, either the complement operation or the union operation. And for the union operation, we have already proved that under the union operation, union of two context-free languages is always a context-free language. So where is the problem? Problem is with the complement operation. So our assumption that L complement will always be a CFL when L is a CFL is not true. So that's why L complement is not always CFL when L is. So L complement is not necessarily a context-free language always. In some of the cases it may be, but not in all the cases. Okay, so as it is not always CFL, so that's why this operation complement is not closed under the for the set of context-free languages. So this is in this manner our complement is also not closed. This operation is not closed for the context-free languages. Now let us take our next operation, that is the difference operation. That is L is equal to L1 minus L2. So L is defined as the difference of two context-free languages. Both L1 and L2 are context-free. So L is defined by their difference. Okay. So meaning thereby it will consisting of all the words which are present in L1 but not present in L2. Okay. So sigma star will always be a context-free language for any sigma. Why? Because sigma star is a regular language, and regular languages are fully contained inside the context-free language. So if a language is regular, it will always be a context-free language also. Okay, so that's why sigma star will always be a context-free language. Now let us assume that difference of two context-free languages is always a context-free language, meaning thereby we are assuming that L is context-free. And when L1 and L2 both are context-free and their difference, we are assuming that that is also a context-free language. Now let us assume that L1 is equal to sigma star, because L1 and L2 both are context-free language. So we are assuming L1 is equal to sigma star, which is a context-free language which is known to us. Okay, so L1 is sigma star, then L1 minus L2 becomes sigma star minus L2. And what this sigma star minus L2 is? Nothing but the L2 complement, its complement. So sigma star means from all the words, if we remove all the words of a language, then the remaining words will be the part of its complement. So it is L2 complement. So it is showing that L2 complement is also context free, because we are assuming that L1 minus L2 is always context free. So sigma star minus L2, that is the L2 complement, will also be always context free, which we know that it is not true. We have just proved that complement of a context-free language is not necessarily a context-free language. So meaning thereby our assumption that a difference of two languages is always context-free is not correct. Okay, so that's why difference of two context-free language is not necessarily a context-free language. So this operation difference is also not closed under the not closed for context-free languages. So these are all important closure properties of the context-free languages which I have discussed. There are many other operations also over which we can test whether the set of context-free languages is closed over that operation or not, but these are the most important ones. Thank you all.